Okay, last of the electric field strength lessons. We're nearly done. Okay, so this is when we have two charges. Okay, again, obviously your charges are going to be in a row. If you've got two things, they're always in a straight line. You can always draw a straight line between two dots. But let's say now we've got two charges. Okay, and we want to know, so here's our straight line. We want to know what the electric field strength is somewhere that is not on the same straight line. So remember in the last lesson we said, well, what's the electric field strength on this line, or over here still on the same straight line. Now we're talking about what if you're interested in determining your electric field strength somewhere out here, okay, or there. But unfortunately for now, at least, we are only actually able to deal with scenarios where you're interested in the electric field strength at a point where it makes a 90-degree angle. Okay, so it's very similar to Coulomb's law with three angled charges in that it looks like a right angled triangle when you've got your diagram. Okay, so this is basically, if you've got two charges, you'll most often see it set up like this, two charges, and you want to know what the electric field strength is somewhere in the vertical plane of that one and in the horizontal plane of this one. So you've got your right angle. Okay. Now it is all, the steps are all written out for you. I'm saying the same thing every lesson. The steps are all written out for you on your notes. I'm not going to write them again, but I will say them as we do them. Okay, let me actually just pause you so I can write down our example and then we'll do it together. Okay guys, so here's your example. There's a whole lot of words that go along with it, but you can read those. Let me read it to you. Okay, so we've got 2 point charges forming a right angle triangle with a point A at the origin. Their charges are Q2 is 6 times 10 to the minus 9 coulombs and Q3 is negative 3 times 10 to the minus 9 coulombs. The distance from A to Q2 is 5 times 10 to the, whoopsie, that should say negative 2. Sorry guys, 5 times 10 to the negative 2 meters. And the distance between A and Q3 is 3 times 10 to the negative 2 meters. What is the net electric field measured at A from the two charges if they are arranged as shown? Okay, so I basically want to know what is the electric field strength here at the points A from Q3 and from Q2. Okay, the net electric field strength. So the way we're going to go ahead and set that up, I just want to make sure I'm doing it exactly the same as it is on your notes. Okay, so we first determine, just like with Coulomb's law, we first determine the direction at this point due to each. Okay, so again, I'm just going to go ahead and draw my arrows. So A, remember, electric field strength is, the direction of it is determined by which direction a proton would move. So if we put a positive point charge here at A, it would move away from Q2 because we would have repulsion. And it would move towards Q3 because we have attraction. Okay, so first thing you do is you determine the directions and a little diagram, right? Yeah, we draw a little vector diagram. Okay, so we've got the electric field strength at A as a result of Q2, so I'm calling that E2. And then we've got the electric field strength going upwards at A as a result of Q3, so I'm going to call that E3. Okay, next up we're going to determine the magnitude of E2 and of E3. Okay, so to do that, we're going, let me not use red, it's too much red. Okay, I'm going to use blue for the calculations. Okay, so to do that, we use the fact that E2 equals K times Q2 over R squared. Okay, then we substitute in. That's 9 times 10 to the 9 times. The charge on Q2 is 6 nanocoulombs, so it's times 10 to the minus 9 over the distance between A and Q2 is 0.05. And don't forget to square. Okay, and when you put all of that in on your calculator, sorry, my calculator's under my couch. I don't feel like getting it right now. What did we get here? 21,600. Shoo, that's big. Okay. 21,600 newtons per coulomb, and it's to the left. Okay, now we're going to do the same thing. So we found E2. Now we must find E3 doing the same thing. So we go E3 equals K Q3 over R squared. We substitute in. So K is 9 times 10 to the 9. Q3 is negative 3 nanocoulombs, but remember when you substitute in for your charge, you omit the sign of the charge. So it's just times 3 times 10 to the minus 9, and the distance from A to Q3 is 0,03. And don't forget to square it. And when we do that, we get 30,000. Okay, so this is 30,000 newtons per coulomb, and we know that it's up because it's attractive. Okay, so that's the first few steps. Next up, we need to now, from our diagram, determine the magnitude and the direction of the resultant vector. Remember to do this. You imagine that this is a rectangle, and we're looking for the diagonal. Okay, that'll be the magnitude of our resultant, and then the angle that that diagonal makes with the horizontal. Okay, so we're looking for E net, which is this guy, and the angle that it makes with the horizontal. Okay, so to find the magnitude, we remember that a rectangle is a right-angled quadrilateral. Okay, so that makes us a right-angled triangle. We can use Pythagoras. So to find the magnitude of the answer, we go E net squared equals, what have we got? E2 squared plus E3 squared. Okay, we sub in. E2 is 21,600 squared plus E3 is, where is he? 30,000 squared. We square root, well, we add these together obviously, then we square root both sides, and we find that E net is equal to, let's find it quick, sorry, 36967,01 newtons per coulomb. Okay, so we found the magnitude of our net electric field strength, or the resultant electric field strength. Now we need to find the direction of our resultant field strength. Okay, so magnitude done, direction coming up. To find the direction, just like with vectors in 2 dimensions, we're going to use trig ratios, and again, tan is your best option. Okay, so opposite over adjacent, which means E3, because that's the same length, E3 over E2. So tan of theta is equal to E3 over E2. Let's sub in 30,000 over 21,600. And remember to shift tan this, to find our angle. And we get that theta is 54,25 degrees. Okay, so we have our magnitude, we have our direction, but now we have to put it all together in a little sentence, just like we did with Coulomb's law, just like we did with vectors in 2 dimensions. We write a little conclusion. Okay, so we're going to say, therefore, E net is equal to the magnitude, which is 36,967,01, at the angle is 54,25 degrees, and that's never good enough. Now we have to be more specific. Is it anti-clockwise or clockwise? And is it off the positive x or the negative x axis? Okay, so here is our origin, which means this is the negative x axis, and I'm going from the axis that way, which is clockwise. Okay, so it's clockwise from the negative x-axis. Okay, in your tests and exams, please write out the full word negative, don't just write neg. Yeah, that's basically it. Again, with these angled diagrams, with Coulomb's law and with electric field strength, when you've got this angle, it's actually quite a nice thing to see in your tests or exams because it's quite predictable. There's nothing scary they can ask with this arrangement. The calculation itself is quite scary, but if you practice it enough, you'll be fine with it. The scary things can be asked when you've got it all in a straight line. That's when you get the scary stuff. Remember when you've got like 2 charges like this and then they want the electric field strength over there. They can ask you all sorts of things then, so it gets a little bit tricky. Okay, yeah, so that's it. Again, you'll probably think you're having mad deja vu. This looks almost identical to Coulomb's law. The only difference is the formula that we're using and the fact that we're calculating electric field strength and not force, electrostatic force. Okay, yeah, so I'm going to leave you there. Next up, we're going to be looking at circuits. Okay, so if you're feeling good with this, please start revising your grade 10 circuits, electric circuits.